Good afternoon, everyone, and welcome to this Nobel Talk. My name is Sofia, and I am a student at Technic and representative of AEIST, the Student Union of Instituto Superior Técnico, that organized this event in collaboration with the PhD Student Club. Thank you everyone for joining us today on World Engineering Day for this unique opportunity to hear from and interact with Professor Reinhard Genzel, 2020 Nobel Prize laureate in physics. So first, I would like to thank you, Professor Genzel, for accepting us to speak at this event. We are extremely excited to have you here with us, and so grateful for this opportunity that represents for technical students to learn and sharpen their curiosity. This is a unique opportunity for many of us to meet a Nobel Prize winner like you. So thank you so much to be here with us. To moderate this sensation, we have with us Gabriel Rochinol, who is physics student at Técnico, and Fábio Cruz, recent Técnico PhD graduate in physics and now researcher at Inductivity Research Labs. So I would like to pass the word to Fábio to introduce our guests.
Thank you, Sophia, and again, welcome everyone to this event. Before we move on to Professor Genzel's talk, I'd like just to invite everyone to write down your questions, any questions you may have, to our speaker in the Zoom chat box, or to raise your Zoom hand, and at the end of the session, we'll either read your questions out loud or ask you to unmute and speak up and ask your question. So today we're very honored to have Professor Reinhard Genzel with us for this Nobel talk. Professor Genzel is currently co-director of the Max Planck Institute for Extraterrestrial Physics, a professor at LMU in Munich, and also an emeritus professor at UC Berkeley. Besides receiving numerous prizes and awards throughout his career, Professor Genzel shared the 2020 Nobel Prize in Physics with Professor Andrea Ghez from UCLA and also Professor Roger Penrose from Oxford University for the discovery of a supermassive compact object in the center of the Milky Way. So again, we're very honored with the opportunity to hear from you about your scientific and academic career. And without further ado, Professor Genzel, please go ahead when you're ready. And thank you.
Okay, well, thank you for having me. Delighted to be there. Tell you a little bit about what we've been up to. In fact, what I will do is to give you a little bit of a travel report. A travel report which, however, took 40 years, at least for me. So that's already one sort of kind of a thing, which is a little unusual, that in the field I am at, the timescales for doing projects like what I will talk about, namely the issue of whether black holes, in particular massive black holes, exist, and I'll tell you more about that in my talk, is something which takes time. It takes effort. It takes a team of many people who've been working with me. It takes technology, which has to be improved on and ever done better. So patience, you have to stay with it. And I tell you, the thing is, it's terribly exciting. I mean, I'm now 70 years old, and I'm burning for discovery in science now just as much as I was a student. And I always have a little bit of a allegory of basically the kind of study we are doing is like exploring a forest. There you go, at the entrance of this strange thing called a forest. You've never been in one. Now you go into it and you discover new things, trees. You discover different types of trees. And of course, you are an aspiring young researcher. So after a while, there's all these impressions you have. And so you begin to want to be a little quantitative about it, and you write it down and make notes and so forth. And so this is the discovery which we in astronomy have been blessed with in the universe, to be able to make ever deeper and better observations, discovering how the universe expands, the Big Bang, formation of galaxies, then of course exoplanets and many other things. Terribly exciting right now. Now, of course, at some point in your march through your beautiful forest, you'll discover some strange regularities. You see there are flowers, blue flowers, red flowers, all kinds of different colors. But then you note that the blue flowers somehow are always on the left side of the path, never on the right side, always on the left side. That's when you, in your exploration mode, of course, your physicist wakes up in you, because now you want to understand, why is it that the blue flowers always are on the left side of the path? So that's what I will do today, or try to do today in this talk, to show you our walk through the universe in the sense of this question of black holes, and then how we have tried, hopefully now successfully, to show that this prediction of these black holes really is something which is correct. Now, you know, we live in the Milky Way. The Milky Way is a disk galaxy. So on the right side, you see seen edge on. So that the disk is about 60,000 light years across. Our sun lives about 27,000 light years away from the center of the Milky Way in the outer parts of the galaxies. There's, of course, also these spiral arms, which have lots of gas and dust, as well as stars in them. And so when we look at the center of the Milky Way, we have to look through, pretty much half of the galaxy. So that's actually one of the technical problems we have to overcome, as I will tell you, when we want to study the center of our galaxy. So that's, so to speak, the kinds of objects which we know exist since the early 1900s, these galaxies, and we know they are full of stars, gas and dust. The Milky Way produces a new star every year. It used to actually, when it started forming 10 billion years ago, produce many more stars, about 100 stars at that time. So there's a history of these galaxies, which you would like to understand, which has to do with the expansion of the universe and how structure has formed in that universe. Now, 100 years ago, as you may recall, Albert Einstein, in a famous meeting of the Prussian Academy in Berlin, presented what he then called his general theory of gravity, of general relativity. And basically here he tried to create a theory to explain how masses interacted with each other. Now, of course, from Newton and Kepler and all the others, we knew already quite a bit about gravity. We knew that you have a sun, say this yellow thing, you have another object around it, which you might want to call a planet. Then if the red object is bound to the sun, then there are so-called orbits, circles or ellipses, which basically then lead to a eternal motion of these planets around the sun. Now, Einstein's theory went a little further than that. in that it basically tried to bring into this the concept of space-time, to describe all of this in a continuum of the three spatial dimensions as well as the time dimension, and also taking into account, number one, that's the speed of light, which is our communication. The fastest communication we have in nature is finite. Nothing can go faster than the speed of light. And the second, that light actually also sees gravity, which was not embedded in the theory of Newton's theory. So Einstein's theory then made this a tremendous new leap of trying to basically say, well, if I observe the sun with my telescope and behind the sun is a star, then the theory of Newton would the sun, basically have just an in-between, would eclipse the star, but the star would otherwise send its light rays in straight lines past the sun. And so, in fact, if it's right behind the sun, you wouldn't see the star. Well, actually, general relativity says, no, that's not the case, because the photons, or the light rays, actually see gravity. They are bent. They're bent by the gravity of the sun, in this case, towards us. So all of a sudden, we can see a star, which is right behind the sun, although it's eclipsed, so to speak. You see it. And when we basically make a measurement of where the star is, then of course you go backwards along the direction which it seems to arrive from. So that's quite a ways away from the sun. So this light bending, he could calculate in his theory of general relativity, and he made a prediction. And so this is 1915, 16. In 1919, there was an eclipse of the sun, of star cluster by the sun, and Lord Eddington and a number of his colleagues went down there to the site in the Principe area near Brazil, and made that measurement. And indeed, they saw the light bending just as Einstein had predicted it. So that showed that there was something to relativity to gravity, which had not been much appreciated. Now, when you look at this a little more in detail, then of course the next thing you notice that, well, how much does this deviation of the light rays around the sun depend on the gravity? And then you find, of course, it is strongly dependent on it. You can put it the other way around and say, suppose you send from the surface of the sun a rocket outward, then you need a rocket to have a speed of about 600 kilometers per second for it to escape from the surface of the sun into space. And that's escape speed depends on the mass of the sun, but it also depends on the speed of the sun. So in fact, if you in your mind make the sun ever smaller, say to about 3 kilometers inside, then all of a sudden the rocket would have to travel at a speed of about the speed of light or greater. But that can't be, because we know experimentally that the speed of the light is the upper speed. So in fact, when the first solution of Einstein's field equations were done already a year later by Carl Schwarzschild, whom you see there on the left side, he found that there is a characteristic radius for a given mass, which is called the event horizon. And at that event horizon, in fact, that's exactly the region where the rocket, so to speak, would have to escape at the speed of light, which is not possible. So light cannot escape. And anything inside of the event horizon, therefore, is hidden from communication with us. So that is what you might want to call a black hole. That wasn't used as a term at that time, but it's clear what is meant. So it's the effect of gravity onto photons. So the next thing took about 50 years as people looked at mathematically the theory of general relativity. And Roy Kerr, the man there in the bottom middle, found another solution, namely that of a rotating black hole. So spin, rotation, as well as mass are, so to speak, two quantities you need to know. And in fact, Roger Penrose, who shared the Nobel Prize with me, and others very quickly showed that other than charge, electric charge, there's no other thing you have to know in order to describe these objects called black holes. Only spin and mass. Everything else follows from that directly. So in other words, a black hole doesn't have hills. It doesn't have a shape to it. Everything you can describe with these two parameters. Now there's another thing which gets really weird when you take your rocket, which we use to fly away from the thing, turn it around, fly into it. Then in principle, if you're very sturdy, you will fly through the event horizon, all right, in your reference frame. But then, that's it. You will not be able to return, of course, because you can't go faster than the speed of light. And in your time frame, you will end up in finite time at the center. You cannot stop. Everything which crosses the event horizon goes to the center and disappears there in a point. So you have a mass and a point. Well, that's a infinite density, a singularity. So that's the next proposal of general relativity, a singularity. Well, that sounds pretty fishy because, we know in physics that people once thought that electrons were point masses or point charges, or that atomic nuclei were point objects. And it turned out that if you had good enough physics and you had a theory, a quantum theory, which on these small scales can describe the objects, then there are no singularities. We don't have a quantum theory at this point of general relativity of gravity, and that's one of the big things in physics. Another one, another mystery is been touched on by Stephen Hawking, who you undoubtedly know, who basically said, well, okay, if you and I stand outside of the black hole and throw things into the black hole, I throw rocks into it, you throw cars into it, some other one throws something else into it, then of course the mass of the black hole increases accordingly. But at the end, general relativity will tell you that everything ended up in the singularity, got smashed there. You won't know who threw what. The history and the knowledge of the quantum numbers, we would say, would be forgotten. Now, every theorist in quantum theory would tell you, that can't be. Quantum numbers are constant. Yeah, they cannot be forgotten. So Hawking, in fact, proposed one way to cheat the system. If at the event horizon you send a photon, a pair of photons or a pair of particles and antiparticles which you generate out of the vacuum through Heisenberg's uncertainty principle, then the particle which makes it out of the event horizon will actually be able to come to us. The other one, of course, won't. But that's a way to send information to us. And it is believed that this information, in principle, codes up the history of the accretion onto the black hole. So there are many mysteries about these black holes, theoretically, which are still around today and makes this field one of the most exciting and interesting fields also for the future. Okay, so that's basically the story I've given you, event horizon. The next question is, how would you make any experiments on a black hole if you can't see it? Well, think of the solar system, and the planets, and the planets are on Kepler orbits, and the speed of of traveling of the planets depends on the radius. In fact, it's like 1/square of radius, the speed, and the outer planets are slower than the inner planets. So if you now in Gedanken switch off the light of the sun, then nothing would change, because the motions of the planets are little affected by the radiation of the sun. They are basically just dominated by the gravity. And so if a second solar system would have been studied by Tycho Brahe back then, he would have reported the same measurements of the planets to Kepler, and Kepler would have had to, or Newton, would have had to make the same conclusion, namely that in this distant system with nothing in the center, there is a one solar mass object at the very center. And then you would like to say something about the size of it. Well, then you have to, of course, hope that there's a planet very close or closer than Mercury in order to make his statements. So that's, in fact, the technique we are using to study the question of whether or not such black holes exist. The first observational signature of these black holes came in a very strange way, namely the radio astronomers were mapping out the sky in radio waves and discovered some very bright radio sources, which then on optical plates, like you see here, look like stars, fairly faint stars, but stars whose spectrum had spectral lines in them, which have lines which you know from their ratios, but are redshifted in this particular case here, 3C273, the first one, of 16%. Now, of course, if you assume that this 16% redshift is due to the expansion of the universe, you can use the Hubble expansion to calculate how far away the object is. And that turns out to be 2.4 billion light years. That's a way over distance, at least at that time. That was a record distance. And so if you convert then the amount of light you see and turn that into a luminosity given this distance, then you turn out to have an object there which produces 1,000 times the light of the entire Milky Way in a region which is merely a light year across. So that was quite astonishing. And the explanation a number of theorists proposed within the next years was paradoxically black holes. While black holes, of course, cannot shine, cannot radiate from within the event horizon, when material falls into the black holes, on the way inwards, gravitational energy can be converted into heat and electromagnetic radiation in the very hot regions right around the black hole, and that could explain these quasars. Well, that's a proposal. As you know, in physics, you can propose whatever you like, unless you have good experimental evidence. Now we cannot travel to a quasar. We cannot even make the measurement of the solar system, which I proposed to you, at a quasar. At least at that time we couldn't. But then Martin Rees and Lindenbell wrote a very influential paper in '71, where they said, well, maybe these black holes exist also in other galaxies, not only this one's 3C273, but perhaps every galaxy has a black hole, just only a few accrete a lot of material so that they shine. In fact, that is what we think now. We think that every galaxy has a massive black hole. And in fact, the mass of the galaxy and the mass of the black hole scale with each other because they have co-evolved over cosmic epochs. If that's the case, well, then maybe even our own Milky Way might have a black hole. And so then Lindenbell and Rees basically said, you observers go ahead and look at the center of our Milky Way and see whether you, from the motions of objects there, see whether there's a compact mass. Well, easier said than done, because if you look at our Milky Way, there's these spiral arms, as I mentioned, and there's dust and gas in the spiral arms, which extinguishes the optical light pretty well, about by a factor 10 to the 12. So actually, unfortunately, in our Milky Way, you cannot use optical lights. You have to go to longer wavelengths, radio waves, but also infrared waves or shorter waves, X-rays. And then you can look into the center of our Milky Way and study the galactic center. So here, let's fly into the center of our Milky Way. You see these dust clouds, which I mentioned easily. So we're going inward now from the location of the sun, flying inward. I'm sorry for the jagged motion. This is the internet, not our rocket. Our rocket flies pretty steadily at 10 to the 12 times the speed of light. And we go inwards, and with our infrared eyes, we can see that in the center of our Milky Way, there's a very dense concentration of stars, about 1 million times denser than in the solar neighborhood. Also very massive stars, very, very impressive. This is sort of one of the modern pictures we can take with sophisticated apparatus on big telescopes, where we see different types of stars, red stars, cooler stars, as well as blue stars. Now, it turns out these stars are not like the sun, not at all. They are very massive. Some of the blue stars are 100 solar masses. But the main thing is we can use, in principle, these stars and see and look at their motions and measure how they move. Also, gas is in this central region. And the radio astronomers discovered in the 70s a compact radio source, which we now know has a size of a mere 40 micro arc seconds. That's about 30 centimeters on the moon, 40 micro arc seconds. That is, in fact, 4 times the event horizon size of a few million solar mass black hole. So that could be, in fact, a black hole there. So that's when in the 70s, the interest grew to start looking at motions of gaseous stars in the center. You have to do that, as I said, in the infrared or in the radio in order to do this. But here you go. There is, in pink, ionized gas floating around in streamers, and also neutral gas, which is the green. And a Nobel laureate, Charles Townes in Berkeley, was at that time one of the few people in the world who knew how to build infrared spectrometers. And he and his students, and I then joined as a postdoc initially and then as a faculty member in the early 80s, measured the motions of gas clouds, and from that then inferred the mass in the center as a function of distance. And on the left side, you see the result at that time. So we wrote a paper in 85 showing that when you go from outside in, then the mass, which is on the vertical axis in logarithmic units, is very large, but then drops. That is basically the extended distribution of stars. But then once inside of about 3 light years, 1 parsec, then the mass doesn't change much anymore. And so you might have a point mass, at least for the resolution of our measurements, of about 2 to 4 million solar masses. And so we actually were pretty courageous at the time. In the Nature paper we wrote, there's a black hole in the galactic center. Well, believe me, nobody believed us because science, how do we know that these gas clouds really are only driven by gravity? It could be magnetic fields, there could be stellar winds pushing the gas around. No, that's not good enough. Also, the 1 parsec is 1 million times the event horizon size. So that's way outside of the event horizon of a putative black hole. Could be something else, could be a bunch of neutron stars. 1 million neutron stars would fit the bill, or other faint stars which might be concentrated there. So nobody believed us. And so when I then moved here to Germany, we started a new program and started building immediately new instruments. Instruments which allow us, first of all, to measure stars and not gas, and instruments which would give us sharper information on the distribution of the material in the center. So we needed to have low noise imaging detectors. It was very difficult at that time. Very few people other than the American military knew how to build them. The next issue were the distortions by the Earth's atmosphere. of the waves coming into the Earth's atmosphere toward the telescope on the ground. Basically, the winds, the refraction and the winds of the atmosphere makes the images unsharp. And the answer to this is the so-called adapted optics. You have to measure through an optical device how much the imagery, the waves are distorted. And then you have to have a deformable mirror to unbend these distortions. Now, this has to all happen on a very short time scale within which the images are changing. So technically, that involves incredibly fast computers and sophisticated optomechanics. And then, in fact, however, you can get diffraction-limited images, as you see on the left side there, from these smeared out, seeing limited images. You get diffraction, and the bigger the telescope, the smaller the diffraction. So at that time, in the late 1990s, the first 10-meter class telescopes started coming in, and we then teamed up with the European Southern Observatory, ESO, which has 4 8-meter telescopes in Chile, and started measuring the motions of stars at the galactic center. Now, sometimes, in order to make the correction going, you actually are not served with a very bright star, which you need to make the correction. So you have to make your own star. So that's why we send artificial laser guide stars into the upper atmosphere, where they get reflected and come back down, and then we analyze the light. So there's a lot of technology which we had to overcome, and so that we are able to see the motions of the stars. At that time, a second group of Andrea Ghez, using the Keck telescope, which also got built at that time, also started. And so within a few years, both groups found that the stars near the Sagittarius star, in fact, are moving. These are motions from pictures of the central light month around Sagittarius star, which is the green cross there, in 3 different years, in red, in green, and in blue. And you can see there are several stars which clearly change their position from year to year. You also see that the innermost stars near Sagittarius star move more than the outermost stars, which hardly show any prism effects. So that's the Kepler's laws in qualitative terms again. The outermost stars clearly see less gravity than the innermost stars. This means that the motions are dominated by a mass in the center, which is concentrated. And then if you look at the magnitude, you see 2,000 kilometers per second for the innermost stars. Well, that's about 100 times the speed of the Earth around the sun. And we're talking about light months or light weeks here. So if you then turn that into a mass, then we're talking indeed about millions of solar masses, but now on a much smaller scale and with a better technique. So must it be a black hole? Well, we are still about 100,000 times or several 100,000 times outside of the event horizon. So the same skepticism that this must be a black hole are correct. We must get closer. Also, we are measuring the mass here from a statistical argument because we don't know where along the line of sight any given star is. So what you really want, you want to measure the orbit of a star. And that seemed pretty far-fetched because the orbital timescales we're talking about are typically hundreds of years. That's too long for even long-lived astronomers. So the solution is nature has to come and help you. And nature was nice to us. It gave us stars, which indeed come very, very close. Here's one of the best ones we have, called S2 or S02. It has a 16-year orbital period and then approaches the galactic center until at its peri there in the bottom at about 17 light hours. 17 light hours is about 4 times the orbital radius of Neptune, planet Neptune. So this is enormously close. And it moves there at about 3% the speed of light, 8,000 kilometers per second. And you also see that the motion which we saw our measurements are in blue, and the motions the Keck group saw in red is pretty much the same. So we agree. There can be no doubt that the motions are correct. And if you calculate the mass near Perry, which was occurred in 2002, you get the same 4 million solar masses, which we had found earlier. Now, however, closer in, and with these very precise methods of a stellar orbit. So I have to ask again, are we sure now that this is a black hole? No, because in order to make the statement that this is a black hole, we have to assume that general relativity applies. Nobody had, at that time, tested general relativity on this mass scale. But we knew that the star would come back. 2002 plus 16 is 2018. So we said, okay, if we, in the meantime, in the next 16 years, manage to improve our equipment such that we are even better in resolution, well, maybe we can see effects of general relativity and come even closer to the event horizon. And that's exactly what we did. In the meantime, both groups, we and also the Keck group, measured the motions of a number of stars. And it was fantastic, beautiful to see that in the very center of the Milky Way, there are many tens of stars very close to the black hole, all on different orbits. Every one of these orbits you can use as a precise instrument to measure gravity. And every one of them tells you the same story. There's a mass of 4 million solar masses. I won't tell anything. I don't have time to discuss the other interesting question. How come that nature was so good to us and gave us stars? That was by no means guaranteed. On the other hand, it was actually unlikely that there be stars in the innermost region. But let me not discuss this and just go on to the next question. How can we get still better? Well, we have 4 telescopes on the mountain, not just one. We've used one of them so far. But if you use the technique of so-called interferometry, where you combine the light from all 4 telescopes, then we know that from radio astronomy, you can get the resolution, the angular resolution of a telescope, which then has a size of 100 meters, not just 10 meters. And that instrument, that beam combiner instrument, we built then under the leadership of Frank Eisenhower in a European consortium over the next 10 years to be ready for the Perry of S2 coming back in 2018. We did make it. And at the next Perry in 2018, we were ready to measure 20 times better in angular resolution and astrometric precision. And that makes a big, big difference because gravity has such sharp eyes. We can measure, basically distinguish 10 microarcseconds, a euro cent coin on the moon. And so when we started early on, we had that kind of a resolution, barely seeing the stars. Then we switched on the adaptive optics, which I discussed with you, and saw individual stars and their motions. Now with gravity, we can now take this innermost region right around the star, which is this asterisk, which is Sagittarius star, and resolve it and see, and this is a picture from last year, that last year there were 4 stars right around the black hole on scales of the solar system. And we can not only measure positions, we can measure motions. But very precisely on a scale of about 100 times the Earth-Sun distance. And the motions are very, very fast. So we can, with great precision, measure the orbits, and from the orbits we can measure the precise properties of the gravitational potential for measurements from night to night to night. So, to come to a conclusion, what did we find? Well, the first thing we found, indeed, as predicted by general relativity, is the so-called gravitational redshift. If you have a star moving around a black hole, then the light has to climb out of the potential well from the region around the black hole towards us out of this gravitational potential. And that means it loses energy, or it is shifted to longer wavelengths. So in this left picture there, when time is on the horizontal axis, Perry was in 2018.3, then Newton would have predicted that gray line, while general relativity would predict that red line, and then the cyan points are the data points. So you clearly we see that general relativity is absolutely the right theory. The next effect is the so-called Schwarzschild precession. In Newton's theory, if you have a dominant central mass and an orbiting other object, stellar object or planet, well then the orbit, say an ellipse, has to be the same in time for all times. Nothing happens. Not so in general relativity. In general relativity, you would predict a precession. And this precession, in this way of plotting it in one coordinate, looks like basically when you come to the when you're way away from the black hole, you're on basically a Kepler orbit, so you move on the horizontal axis. But once you're near Perry, close to the black hole, the precession is very fast. So this looks like a kink in the orbit. So the red line again is a prediction by general relativity, and indeed we see that, and you can verify that this Schwarzschild precession is indeed exactly what general relativity predicts. By the way, this also tells us that there is not much other than a single massive black object. There's not a sort of it's not a double, or it's not, there are not other very massive objects surrounded. It's a single 4 million solar mass compact object. And then finally, we can also see gas close to the black hole, near the event horizon, moving when material falls into the black hole. And from that, deduce the properties of the gas and the central mass. We see a motion of these gas clouds on scales of about 10 times the event horizon size. And that's exactly what you would expect from the black hole paradigm. So here's the story of the 40 years. When we started, in a diagram where you have, again, mass on the vertical axis in logarithmic units, and then size away from the center of the mass in horizontal axis, we were just barely seeing the deviations from an extended mass in the outermost stars. And since then, we've been continuously moving inward, always using stars or also gas to show that the mass inside ever closer regions towards the central region is always the same 4 million solar masses. And from that, we have quantitative information that the object indeed is consistent to all extent quantitatively with a black hole of 4 million solar masses. And in fact, general relativity is correct. So why then did the Nobel Committee not say in their Nobel Prize document for the discovery of a supermassive black hole? Well, they're correctly very cautious, just like I've been throughout my little 40-year trip for you, because we have not yet shown that the Kerr metric, remember the solution, the general solution of a rotating massive black hole, is really truly true at the event horizon. That's what we would have to do. Now, we do hope that this may be possible through another technique, radio observations, looking at the so-called photon orbit, and also through gravitational waves. Maybe not in the galactic center, but in other regions. We ourselves are currently upgrading gravity to ever more sensitivity. The radio astronomers are using now the telescopes across the entire world to resolve the black hole in the galactic center and elsewhere. In a few years from now, Europe will have a 40-meter class telescope, the so-called ELT, and then in 20 years from now, the gravitational wave community will be able to see the in-spiral of supermassive black holes and test the theory then. It's an exciting story, and one, as I said, which will go on. There's so many questions which we have. Is the theory really truly there, truly correct? How did these massive black holes come about? How did they grow over cosmic time? Are there intermediate mass black holes? Are there primordial black holes? And how did this all get started? And is the theory of general relativity really true? So that's my report of a 40-year journey.
Thank you so much, Professor, for sharing these great bits of your research and your career with us. Unfortunately, Gabriel had to leave, but I'll be joining Fabio asking questions now. We'll start maybe with some general questions, and then while we wait for audience input. So our first question is, how can the general public relate to your discovery with their daily lives? Or alternatively, how do these findings affect our lives?
Well, I tried to sketch that in my introduction. Surely the more technical parts of what I told you about is something which may or may not be of interest to people of the general public. But the forest will, because we human beings are curious. And that's what makes us humans, that we want to know, we want to understand how the universe works, what is in there, and get a picture of can this be all understood. And the discovery, of course, of all these things, which I mentioned already at the beginning of the talk, is mind-boggling. An old science like astronomy, which already was done thousands of years ago by the first civilizations of humanity, is still going on and is one of its most exciting parts. And I think the general public sees that, this excitement of new discovery.
Thank you so much. And now for a question from the audience, Pedro asks, in your opinion, which was the most groundbreaking paper / discovery in the history of black holes? Other than yours, of course.
Oh, no, I would say, we had a tremendous luck, I would say, that after, let's just keep it in mind, 100 years after the theory was created, and 50 years after the first astronomical evidence for possible such objects came into the vision of astronomers, we were part of several attempts to actually go at this as you would in a laboratory. Now, we cannot fly to a black hole and make measurements as physicists would in a laboratory, but we can, as I've tried to sketch to you, make very precise measurements now with gravitational waves, with electromagnetic waves, which come close to laboratory tests, and thereby make the weight of the evidence ever greater. Now, I've tried to explain to you that one has to be cautious. One should not, yell out too early success, if there's still some possibilities that, there may be other things. And I would keep to that. And that's why I say we're not at the end of the road yet.
Thank you so much. Now for another more general question. As we know, the research path can be full of obstacles and failures. So we were wondering if you could tell us about one of your struggles in this journey that in the end might have led to the important recognition, as the Nobel Prize.
Well, okay, I think, there's certainly the case that when you build experiments, and I've been involved over my career in building 25 big astronomical instruments, both on the ground as well as in space, not everything works. Sometimes catastrophically. Sometimes we had to give up and just stop an experiment and turn elsewhere. Fortunately, in the Galactic Center, I have to say, while we have seen some failures of a detector or laser or something like this, we could usually recover and find a solution out of it, and or pick up a different route. And as I said, nature has been good to us. I mean, sometimes you cannot demand that these kinds of measurements are possible in their sort of ultimate purity, which you would like to do in physics. But we were lucky in that sense. But sure, you have to fight. Now, when I was a young person, I did a lot of extreme sports. I wanted to go to the Olympics in Munich, and I think that was a good training for becoming a research scientist, because as you know, if you want to do extreme sports, then there too you better be at it. And if you break a leg, or your muscle goes awry, that you continue and stay with it.
Thank you. Wonderful. We're a little over our time now, but if you have a few
Sure.
more minutes, and
Sure.
we have a few more questions. So I wanted to ask you a bit about your interaction throughout these years with your team and your students. So in your early career, like you said, you were a postdoc at UC Berkeley, and you worked with Charles Towns, who was also, as you also noted in your talk, a physics Nobel laureate as well. So the question is, how has this interaction shaped the way you did the research in your career, and was this interaction with his students any similar to your interaction with your students?
Yeah, no, I think that's an excellent question. Let me start with the team, so to speak. As I mentioned already before, what we have done here over these 40 years, I surely wouldn't have done by myself. Absolutely not. I'm just, a trainer of I will say sometimes I'm a trainer of a Champions League football team, and my job is to keep everyone together. Of course, I like to kick the ball from time to time myself, but by myself I cannot, win against if Barcelona or whatever in football, or Lisbon for that matter. And so it's been absolutely fantastic to see young people come in and continuing to come in and be very excited. And we have a young Portuguese student coming in this year. In fact, maybe I saw his name on the list of listeners. Is that right, Diogo? Are you there? Yeah. Anyhow, I mean, it's been just fantastic to see that. Now, Towns, I should say, mentors are, in my view, absolutely essential in science. They are a little questioned these days, of course, because the worry is that mentors might have too much influence. I must say that is not the case. I had two mentors. The first one was my father. My father was a physicist, and I learned so much from him. In fact, I did my first experiments with my father in physics. Likewise, the style of research, how to do research, what questions to ask, and in fact, when to stop. I learned from Charles Towns, and I think I very much, in that sense, a copycat of what I've learned from Towns. Now, of course, the experiments which Charlie did at that time were so much smaller than what we are doing nowadays. So there's a difference in scale, but still, I mean, he was just absolutely incredible. I mean, of course, for those of you who have not heard his name, he got the Nobel Prize for the development of the maser and the laser. So that's, one of these things where something which we would say now, oh, well, that's important for technology and medicine and measuring time as precise as you can. Well, times, of course, what he was interested in is he wanted to understand molecules. And molecules have transitions in the radio to infrared range. And so he wanted to have a lamp, a spectral lamp, so that he could, look at the transitions of molecules. And such lamps were not available in the market. So he built himself a lamp. And that turned out to be the maser and the laser. And it's this kind of influence to basically say, well, if something doesn't work, you really have to invent it. You have to go at it. Now, you have to be clever, of course, sometimes, not to go down avenues which are so difficult that you will never get at it. And I've certainly gone sometimes some avenues which, as I said, we had to stop afterwards, and they were not the right ones. But fortunately, not too many times. And I think, again, I learned a lot from Charlie Towns, how to prevent to take the wrong path in the forest.
Oh, all right. Yeah, thanks very much. We have another question from the audience, from João. João Pedro. He asks, what was the most satisfying moment of your career? And I would add, of course, if it was the Nobel Prize, or if like the other discoveries before that.
Yeah, I wouldn't single out a single one. I think because, as you might imagine, first of all, I've described 40 years. I mean, there were many good moments. Perhaps, I guess I could say when in 2002, completely unexpectedly, this star S2 did the turn. That was one of these moments. And the background here is that the prediction is that young stars, which we know in the Milky Way, form normally from interstellar dust and gas, from the gravity of interstellar dust and gas, cannot easily form near a black hole, just because the tidal forces, gravitational forces from the black hole, prevent an extended the gas cloud from collapsing. Okay, so that's why one would not expect young stars, and therefore bright stars, to be so close to a black hole. And the fact that we saw there was one, and nature had put it on an orbit which we could measure in a human lifetime, was pretty special. And also it was so obviously easily to interpret. In fact, I used still millimeter graph paper at that time to plot the data points on a graph paper and estimated by hand the properties of the ellipse, and used Kepler's laws to measure the mass that way. Okay, well, it's not what we do now. We, like you people, we use computers and Bayesian analysis. But at that time, it was so simple to get at the right answer. That was great.
Definitely different times. I guess I have another question related also, I guess, to some of these most satisfying moments in your career. If you could describe the moment in which you got the call from the Nobel Committee, how did you know, and what was the reaction at that time?
Yeah, well, okay, this is a little bit more complicated than you might think. What happens is basically the Nobel Committee prepares these cases over several months. they have, basically several people looking at different cases and then prepare them, and then they basically reduce the list of cases they look at in a sort of a specialty committee. But at the very end, on the day of the announcement, in fact, the entire academy in the field of physics, in this case, then votes. Okay, so that's the critical moment when the vote is taken. And so what they do is they, in the case of physics, they make that vote in the morning. Then when it's clear, they then call the secretary of the Nobel Foundation and makes the call to the Nobel laureates if he can reach them. Typically it's several, in my case 3. And this is not as trivial as you might think. I mean, okay, I got called at 10:30 or so in the morning. I was in a meeting on Zoom, in fact, of the Max Planck Society. So for me, it was relatively easy to pick up my telephone here and then say hello. But then other Nobel laureates, they sometimes can't reach. In fact, in my case, I think Andrea was asleep when they called her, and some other. I know of other cases they were, not available on any kind of a communication device. Other people, and then of course the Nobel Committee has to delay, and so that's what happens. I mean, sometimes they announce that they will make the announcement at 11 o'clock, if possible, or later. The or later comes about normally when they can't reach one of the Nobel laureates when they try to call him. But in my case, I was a mere 10 minutes. So they called me, and the secretary told me, and I was stunned. I was stunned because I never would have thought that I would be a candidate. I know that I had been a candidate early on, but then at that time, felt another case to be the more important one. And so then, if you like, instead, I got the so-called Crawford Prize, together with Andrea Ghez, in fact. The Crawford Prize is, in fact, a prize of the Nobel level, also given out by the Academy, for fields outside of the Nobel fields. And so now here it gets pretty tricky, because in the rules of the game as spelled out by Nobel, he excluded a number of fields from a Nobel Prize, as you know. Mathematics never got a Nobel Prize. And in fact, I believe there's also a rule, or was a rule, that cosmic phenomena, which you can only observe, are also exempt from a Nobel Prize. So that's why discoveries in astronomy really could not be given Nobel Prizes. And if you think about the last century, for instance, the expansion of the universe, Hubble, he didn't get a Nobel Prize because of that rule. Over time, the Nobel Committee changed its mind on this, and surprisingly, in the last 10 years, 5 times or 4 times the prize went in the direction of astrophysics, which tells you a little bit about how exciting astronomy right now is. And maybe there's also been a change of mind amongst the Nobel Committee.
Yeah, definitely a very, very hot topic, and has been for a long time. So yeah, very interesting. So and I guess the follow-up question is, okay, what happened? How did your life change after that moment? Like you were telling us before the call offline, but if you could share it with the audience as well, that would be great.
Yeah. Okay. Well, given that I really couldn't believe it, I thought. I remember at that time that this was the first COVID winter. I sort of felt, oh my God, now COVID hallucinations have taken hold of me or something like this. Then, of course, they tell you, you cannot tell anyone. until the official announcement. And the official announcement is on 11. You can look at it at your TV. But I was in this Max Planck committee, okay? And I had to explain to them why I was now having to leave. So I said, I have something else to do, and I can't tell you what it is. But if you want, you can switch on your TV in about 20 minutes. Of course, everyone on the committee knew immediately what was up. Then the committee makes the announcement, and then all hell breaks loose. From then on until, in my case, way past midnight, because after the TV and the TV crews, we had a press conference here. All the radio stations, everyone wants to talk to you, and then at midnight, I made an appearance in Berkeley, because of course also the Berkeley people feel that I sort of am part of their thing. And so, yeah, I was busy until 2 a.m. in the morning, and the next day the same, and the next day the same, and it's pretty damn hectic. And I've given, fortunately not having to travel, I've given about 60 scientific talks in the last year. So that's a lot. Of course, I'm delighted to do this. I've talked to so many journalists. There's a danger in all of this, that you basically begin to think you know everything. That's when you might step the red line. I mean, I've just signed a declaration of 100 Nobel laureates against the invasion of the Ukraine. That's a touchy thing, because then the journalists want to talk to you about Putin. My God, what do I know about Putin? I have nothing to say about Putin other than I find it disgusting what's happening. Yeah, but you see what I'm saying. I have to, there's a fine line that we don't know everything. We just know a little bit. I know hardly anything. Plus, I'm an old man. I forget everything half an hour after I've said it. So,
I see. Yeah, I wanted to finish. I wanted to come back to something you touched on a few minutes ago when you were talking about the rules, or kind of the rules that exist for attributing Nobel Prizes. This is more like a speculative question. So, as you know, these Nobel Prizes, at least in physics, they are attributed historically to more theoretical or experimental research. And the question is, if you envisage that in the future, it may be also attributed to work done based on computer simulations. As you know, this is now seen as the third pillar of scientific discovery. And so, in your opinion, will it ever award Nobel Prizes?
Why not? I would say computer simulation can be as powerful, or more powerful, in fact, than a simple analytic calculation. It cannot, I believe, or will not easily replace thought. I mean, there I'm a little more skeptical, because if I want to be a little cynical, and forgive me for that, if you program your search algorithm with cats and mice, and there's a dog all of a sudden in the universe, you won't see the dog, because you've trained your artificial intelligence to only see cats and mice. So I mean, I think in that sense, I'm with you. Clearly, the analysis, interpretation of data which we are resting on very modern, sophisticated analyses, in part supported by simulations, of course. In astronomy, it's a give and take, because the complexity of the physics we are encountering in many regions is so high that you cannot describe the phenomenon just by a simple analytic idea, and so then a simulation could be essential to show, this data set, which was interpreted in this way, indeed plausibly can be understood by theoretical ideas through simulations.
All right. No, thank you very much once again, and I'd like now to give the word to Sophia to close the session.
Yeah.
Thank you.
Thank you. So unfortunately, our interview has come to an end, but it was a pleasure to have you, Professor Genzel, with us in this virtual session, and we wish we had more time to talk to you about findings and about our past and ongoing scientific research, but for sure we will have that opportunity in the future. Union of EST would like to thank you so much on behalf of the student present here for having taken some of your precious time to be with us on this special day.
Yeah, I'm delighted to do it. Okay, it's great experience to talk to you.
It was a pleasure to have you in this special day, the World Engineering Day, and for this special opportunity and having taken some of your time to be with us. It was a pleasure. So thank you so much. I would like to remind the others that we have another Nobel Talk now at 4 p.m. in the same Zoom link. We count on everyone's presence. See you soon, and thank you all for your presence, but a special thank you to Professor Genzel. Thank you so much. Bye.
Okay, bye.
Thank you, Professor. Thank you.